And today, Wes is going to talk to us about thermochronology of the McClure Mountain Syenite, characterization of new helium thermochronometers, and constraints on the cooling history of the wet mountains, Colorado.
Well, good morning, everybody. Thanks for coming out this morning. My name is Wesley Weisberg, as Aisha introduced me. I work this summer with Dr. James Metcalf and Dr. Rebecca Flowers. Thanks for being here this morning. And we worked basically on what we're going to talk about today is uranium-helium thermochronology and its application to regional geology and possible constraints on new thermochronometers. In this picture in the background, you can see the wet mountains of Colorado. Well, we're in the wet mountain area, and to the west is the Sangre de Cristo Mountains. And then this rock that Dr. James Metcalf and myself are analyzing it's important, and we'll talk about it later, though, comes into play. So what we're trying to do is to better constrain the thermal history of Colorado's wet mountains and also develop new ways to study those thermal histories of the wet mountains. So the way that we do this is by the use of radioactive decay, measuring that helium ejection. So this is a graph or graphical representation of uranium to lead radioactive decay. And you can see over time you have helium that's being ejected during each of those steps of that decay. And so we measure that helium amount, and we can study the thermal history of that unit. So the actually amount of helium that's retained in the crystal itself is a function of what we call closure temperature. So you can actually see the uranium to lead correlation here as the process is going forward and we're collecting helium atoms. So closure temperature is associated to, it's a mineral to parent age, and we can age date a unit based off of that. So this graph is a representation of, as temperatures are hotter, we actually have a higher amount of helium that's being released into the medium that surrounds, and then as we reach that, as temperatures start to cool, it actually gets to that closure temperature level where helium starts to be retained within the crystal lattice itself, and we can measure that from that point and derive thermal histories. We can derive things like rates of timing of exhumation, thermal histories of rock units, also look at tectonic fault interactions, reburial of areas, and paleotopographical data. And all this information we can build together to help show that picture of the thermal history of a unit of a rock unit in an area. So how does uranium, thorium, helium thermochronology relate to closure temperature? So thermochronology tells us a geologic story over time. And on the left here, you see a graphical representation of geo and thermochronometers. You have uranium, lead, argon, fission track dating, and helium dating. And you can see that right now, currently, uranium, thorium, helium dating only tells us the low temperature thermal histories of a unit. So the way I like to analyze it and think of it is that uranium lead dating is like the birth certificate of a unit. So that's actually where it started out. That's its birth certificate. And we're trying to find that thermal history, which is like the photo album of the unit. And we're trying to build those pictures together to kind of portray that whole unit history. So that's one way you can think of it. So the way that we're going to model this is by using this hefty program from this one particular created by Stanley et al. At the University of Colorado. She was showing the thermal history. So this is the point here when the closure temperature was low enough to retain the helium, and we start seeing that temperature time path, which during exhumation we actually see different time paths of possible ways that unit actually made it to the surface. So that's the cooling over time. So you have time here to current, and then on the y-axis you have temperature to surface and placement. So as we know that as you go deeper in the crust, it starts to get warmer. Near the surface, it's cooler. So we can actually correlate that to different closure temperatures at different depths in the actual subsurface. And so things we can think about too is also reburial and fault interaction that can reset those mineral grains and release that helium that was trapped up inside those mineral grains. And that's not a bad thing because that tells us the thermal history of the rock, gives us one more thing to kind of add to the overall picture. So what we want to do as well is to develop new thermochronometers. Right now, currently, apatite and zircon are the only two minerals that are mainly used, and we're trying to build that overall picture so we can constrain these additional time periods, so we can kind of see that full picture of what's going on in the subsurface, how that rock got to where it is today. So we want to be able to use these different minerals because not every rock has the same chemical composition. And so to use these different minerals, we can date more places with thorium-helium thermochronology. So questions that we want to ask are, will the McClure Mountain Syenite thorium-helium results constrain a more complete picture of the regional geologic history? Currently, this rock is used as a geochronologic standard. However, the only outcrop is from a boulder in a parking lot. And we want to be able to identify a comparable outcrop. So, and then this is the boulder in the parking lot that's used as a standard here in the background. And how can we develop new minerals to be used as thorium-helium thermochronometers? So this is the location of the McClure Mountain Syenite. It's in south central Colorado. It's about 13 miles west Canyon City, and by the little dot of the star here. And this is a geologic map of the McClure Mountain Syenite that I constructed using overlay of two older USGS geologic maps. And so you can actually see the red is the unit, and it's approximately 524 million years old. It's a nepheline biotite syenite hornblende intrusive to the area. And what's interesting is this rock unit is about 3 times younger than its surrounding lithologies. So the surrounding units around it are about 1.3 to 1.4 billion years old. So we actually have an interesting story, if we could figure out the story of this unit, that we could help overall kind of pull the picture together of the regional geology in the area. So this star is actually the location of where our parking lot boulder is that we use as a standard. And then our sample location, 1401, is about a little ways to the southeast. And we actually collected 2 other sample sites as well, but due to time constraints, we weren't able to actually run those samples, but we plan on running them in the near future. So the methods that we actually use for this is basically our big objective is to take big rocks, crush them down into small rocks, retrieve the heavies out of that. That's what we want to do. So first we have hand crushing. Then we pulverize those rocks into finer grains at about less than 500 microns. We sieve those out. After that, we use what's called the Wesley table. This is our first step where we actually take heavies and lights and fluff the lights off and start retrieving the heavier material. Next, we use the Franz, is where we induce a magnetic field on the actual grains themselves, and we can further break those different types apart and get different grades of heavies. And next, we use heavy liquids, which is a lithium metatungstate, and we run that through a centrifuge, spin it around, and the heavy minerals go to the bottom, the light minerals float on top. We can further separate that into the point where we actually can do hand separation. So this is where we use the magnifying. We put it under a microscope, and we pick out the suitable grains to be used as degassing grains. So these are actually pictures of apatite that I picked for the actual study. So next, after that, we degas the grains using what's called the alphachron, which is this machine here. We put it into the machine, and we actually heat it up with a laser. So going back to that closure temperature, we release all that gas that was stored up in that mineral grain, and we collect that gas. And then we take the grain itself, dissolve it in a strong acid, and run it through the mass spectrometer here. And then we measure the uranium-thorium ratio. And then with all that data, we can put it together and build a thermal history. So going back to our previous questions, will the McClure Mountain Syenite thorium-helium results constrain the geologic history of this area? So this is kind of a complicated graph, but I'll try to walk you through it a little bit. So right here we have uranium-lead titanite, and zircon. This is the initial what they used to date the area. So that's how we got our age, about 524 million years old. But we don't know anything below about 450, 500 degrees Celsius. So we don't know the thermal history during its exhumation process to surface emplacement. So you have temperature on the side, on the y-axis, time to present on the x-axis, and we see these are each one of these colored pathways are possible thermal histories and possible time paths, how that unit got to surface emplacement. So, and then these bars here are different closure temperatures for different minerals that we use to help constrain that overall geologic history. And then you see here we have missing gap areas. So if we get more minerals, we can actually fill in those areas and have a complete picture and give us a lot better idea of what's going on. So these are the different time paths. Okay. And then our next question was, can we find a comparable outcrop to the standard boulder that's in the parking lot? And we actually did. There's me breaking them up and getting samples out in the field. And then how do we develop new minerals such as titanite and bdelliite to be used in euthorium helium thermochronology? These are some of the different minerals that we used that we got out of the rock. It was actually really interesting. There was a huge, fairly large different compilation of minerals in these rocks that we have that can be used in euthorium helium thermochronology. So, and also was really nice too is really reproducible dates from the standard. So, and also each one of the dates not only being really reproducible, but that also fell via its correlated closure temperatures within that range. So we have this really great kind of thermal history that we can build with the data that we got from these minerals. So, and then we have some new minerals we need to use the EDS on and kind of further take that down the road and see what we're looking at and if we can even use it for euthorium helium thermochronology. So this graph here that we see is effective uranium, and it shows the amount of, and what effective uranium is it's a proxy for radiation damage, and it's related to closure temperature, relation to closure temperature. So we actually see here with a lower amount of EU, which is effective uranium, correlates to younger ages, and then with older ages correlates to a higher amount of EU. So, and that relationship is linear, we can see here, and we'd like to get some more data to kind of fill in that even more, but we're actually seeing that it's a correlation between the two, so it's quite interesting. Here's the actual model that we were able to create using a program called Hefty, using the McClure Mountain Standard apatite and zircon time temperature path that we see here. So this is, again, it's we have temperature on the y-axis, time on the x-axis. So this here is the point of where the closure temperature of the minerals started. And then we see a relatively rapid cooling for the first 30 million years of this unit, and then to its emplacement here, and relatively slow cooling for the next couple 100 million years. And then right around the end, around 150 to 100 million years ago, we see a little more rapid cooling again to current emplacement and at the surface. So we actually got some interesting data here where it actually started to come down. So each one of these, I should explain, each one of these lines here, the green line is acceptable fits, and the magenta line is good fits, and that's just all the program uses to kind of correlate all this data to create a time temperature path. We actually got very good constraints, and the blue line here is related to the mean of the entire model. So could it be related to the ancestral Rockies? We don't know, but it's interesting to kind of divulge further into, and laramide possible uplift. So going back to that thermal history map that we had before, we actually see the actual thermal history of the McClure Mountain Syenite here by use of the different minerals that we were able to degas and dissolve in acid and figure out the actual dates. So we actually see some interesting things like apatite. This is from the sample collected, and this is from the standard. We see about 100 million year difference, which is interesting. So could there be fault interaction or reburial to play there from ancestral Rockies? We don't really know. Or from laramide. That would be something that we need to discuss further and look into more. So it's quite interesting. So where we want to kind of go with this is analysis of the remaining samples to compare and contrast the collected versus the standard samples. We also, could ancestral Rockies reburial and faulting be contributed to the apatite age difference separation there? And then where did that parking lot boulder actually come from? Because it's kind of an assumption to use something as a standard but not have the actual outcrop where it actually came from. So we really want to kind of find that outcrop and compare. And actually, interestingly enough, from our data from 1401 that we sampled, they're not really kind of coinciding with the actual boulder and the sample. So we want to run the other samples, see where we're going with all that. And is there a difference in chemistry from the McClure Mountain Hornblende standard and the McClure Mountain Syenite samples? And that's kind of the direction we want to move forward with this. Has a lot of different avenues we can go with, so we're excited. And I just want to say thank you so much for making this possible for me to be here. It's been such an amazing summer. So thank you very much for everybody.
All right, thanks, Wes. And I just have to say, I can vouch. That really was a club soda.
Yeah, it wasn't. It looked like, they kept thinking it looked like a beer.
Yeah.
Yeah, exactly. That's beer and club soda, though.
Any questions?
Okay, I've asked you this question before.
Okay.
But I want to know, do you think, do you have any constraints on the emplacement depth of the McClure Mountain Syenite? I know you've seen over that 30 million years, the first 30 million years of its thermal history, it's got rapid cooling. Is that actually exhumation, or is that just cooling to the ambient temperatures of the crust around it?
That's another thing we don't know, and we want, hopefully with more data, we can kind of put that together and find, did it actually intrude rather quickly and cool slowly, or did it intrude slowly and still cool slowly? I mean, we don't really know that. I mean, it is an intrusion into the area, so it'd be something interesting to kind of look into to see that initial first, like, 30 million years. And that's also, if we get, let's see, I'll go back to that slide. If we can get new minerals, utilize new minerals in euthorium helium thermochronology that can kind of constrain those older time paths and apply that to this program Hefty, have new applications to be able to model that, because right now this program is limited to just apatite and zircon modeling. So if we, and I think they're trying to do some titanite, but I'm not sure. It's not done yet, but so if we can add that into there, we could actually see a more complete picture of those older, that older thermal history. Really interesting. I mean, this is going all the way back to Cambrian time. I mean, you're really close to the Precambrian Cambrian boundary there. So I mean, this is a huge amount of time that they're analyzing. So it's really interesting. So.
Thank you.
Oh,
okay, Bob.
So this 150 million event is kind of intriguing.
Yes.
And you wanted to head toward implication on laramide tectonics.
Possibly, yes.
And I guess the other tectonic event from a timing standpoint would be severe orogeny.
Yeah.
So why did you pick moving the laramide to a much older event versus calling on basement involved severe tectonics?
You know what? I actually probably should have put severe or laramide, because this whole area right here, I mean, and also where I was thinking, if you look at the location to where this area is actually at on the western or on the eastern side of the Colorado Rockies, it just made me, the severe was more west from where the laramide actually was, so that could, maybe that's why I was kind of thinking initial uplift, because this was still, I mean, I think the average is for every 1 kilometer you go down in depth, it's increased about 25 degrees Celsius. So we're looking at around 100 degrees Celsius, about 4 kilometers down, roughly. So was this initial uplift the start of the laramide from the Farallon plate crust pushing that up a bit, or was this? It could totally be interpreted as possibly severe orogeny from way off in the west, kind of. But at that time, everything was more compacted anyway. So, you know, I mean, I definitely think that could be a possibility of severe orogeny implications on this area here. So I wouldn't count that out at all. So you're absolutely correct in that.
Oh, Glenn?
So looking at this diagram, I calculated that it's about 4.3 degrees per million years in that early rapid cooling time period. Can you now use that information to say something about the size of the intrusion?
I'm not really sure. You're talking about the actual McClure Mountain intrusion, that actual body. And was it bigger? Is that what you're saying? And maybe eroded away, or it's interesting actually in that area. There's actually other syenite intrusives. They're the same composition. So are those of the same age? I'm not really sure. And so I don't know if that's what you were kind of getting at to that. Other than that, I'm not really sure how to answer that question. Sorry. I'm not really sure if I know. Mhm. Mhm.
The thing was intruded and it was liquid at some point.
Yes.
And
yes.
it had to cool.
Yes.
So if it's cooling at a specific rate,
Mhm.
can you say something about the size of the body?
Hmm. I don't know, Jim or Becky, if you guys want to elaborate on that more. I'm not really sure how to.
I think one of the questions then is, how deep was it intruded then? Because then that would also influence how fast it cools. But the fact that you see pretty rapid cooling shortly after emplacement, as documented by some of those other thermochronometers, would be consistent with relatively shallow emplacement in the crust. I would say probably shallower than that, actually, based on the zircon data. Yeah.
Thank you. All right.
All right. Well, we have a 7-minute coffee break now. I ask everyone to join. No, discussion is good. I like it. I ask everyone to return here, be ready to go. Thank you so much, Wes, and we'll see you shortly.